Hi, welcome to my nuclear structure and radioactivity presentation for Svetlana Barkanova's Physics 2056 Modern Physics class. I'm Xander Mandy, your presenter this evening. A bit about me before we start. I'm a third-year Bachelor of General Science student at Memorial University Grenfell campus in Newfoundland. The thing about Bachelor of General Science is I got to pick 3 streams. One of the streams I picked was chemistry, the other math, third one was physics. So did a bunch of physics up until this point, got to do a bunch more afterwards. Everything beforehand, before this course anyway, was based around classical physics. So how far does a ball move if you smack it with a baseball bat, stuff like that. Projectile motion, kind of boring actually compared to this course. Quantum physics is so much more interesting. It's really the interesting physics, in my opinion. Whenever it was invented, 1900s, I thank them. It's a lot more interesting. My experience so far has been not the worst, not the best. It's not hard. It's just a lot of information. It's like math. It's a lot of math, but it comes with theory, application of that theory, and lots of other information. And in a way, when you do understand it, you get the same feeling when you know you're going to ace your math test because you understand it. And suddenly it's not hard anymore. You got to put in the effort, got to understand it. Now, this is my first course where things cover the quantum side of things. And that's what makes it fun. Physics is fun. Take it from me, I'm more of a chemistry guy. Physics is pretty fun when you understand what's going on. And that's why you gotta practice when you do it. Now, I'm gonna go over the content of this presentation. First off, motivations. Why do we need to know about the structure of an atom? Why do we need to know about radioactivity? What are the applications of this? The simple question that everyone asks every scientist when they discover something new. What's the point? And that's what I'm going to talk about first, the motivation. Why do we want to know this? What's the point of knowing this? How do we use it? Now, nuclear structure is going to cover a couple things. The formation of nuclei, constituent particles that make up the nucleus, forces inside the nucleus, like strong force, bonding in electrons, passing mention, because this is more focusing on the nucleus than the atom as a whole. The proton drip line, it's a little of an interesting topic, a little advanced, but I think it's an interesting tidbit. And fun facts about fusion fission, if you don't know what fusion and fission is. Radioactivity is going to cover a couple less things, but there's more information in that one anyway, because it's specific. The 3 different types of decay, what photons are, stabilization due to decay, weak force, stuff like that. Now, talking about why nuclear structure is important. It's important because it explains the behavior of atomic nuclei, which make up matter. Any atom makes up matter. All matter is atoms. That's all we are, really. We're building blocks, if you want that comparison. And at the center of each element that we're made of, carbon, silicon, whatever, there's atoms. At the center of those, there's nuclei. So it's important to know what nuclei are because they're kind of the main center of the things that make the world around us. They help us understand things. They help us explain and develop things. So we need to know what they are and how they work because the progress we made with that information is quite impressive in my opinion. Applications of it include medicine, pharmaceuticals. By knowing the structure of atoms, how they work, how the nuclei works, you can make medicine, stuff to treat illnesses. That's important. That's pretty impressive. The common cold, I wish they'd get rid of that already. I'm sure they will. Probably not in my lifetime, but hopefully the next one. Industrial materials, tubing, cable insulation. Got to know how those things should work because you don't want to insulate a cable with another conductor. You got to get something that's not going to conduct electricity. And technology, nuclear power. Nuclear power is more of a radioactivity thing, but radioactivity being a whole subset of the applications of nuclear structure, it counts. Now, why is radioactivity important? The subset of nuclear structure. It helps us develop further insights into the structure of atoms and how they change, because this is the major part of like nuclear structure. The picture involved, I don't know what that element is, gotta be honest, but what it's showing is radioactive decay in a cloud chamber. A cloud chamber helps you see radioactive decay because the particles it fires off become visible in the clouds. You can build one of these on your own. There's tutorials on YouTube. The radioactive source you'll probably have to source yourself. I, for one, don't know where to buy it. And if I could buy it, it's probably hundreds of dollars. Now, there's a bunch of applications of this. Some pretty important ones, actually. Medicine, you use it to treat cancer. Well, there are two ways it's used to treat cancer. Active radioactive bombardment of the cancer zone, but picture involved, I'm more referring to MRIs, scanning for the actual cancer. It uses X-rays. X-rays are radioactive. They're a radioactive emission. X-rays are caused usually by some kind of radioactive thing. And it's used to view the insides of people. That's so helpful. Easily one of the best inventions mankind has probably ever made. Until probably will be dethroned by an actual cure of cancer. You can use radioactivity to date objects. So based on how much should have decayed or how much has possibly decayed from an object, you can determine how old that object is. So like how much is either there or missing of this substance, this radioactive material that's supposedly supposed to be there. You can date fossils, you can date trees, you can date Otzi the Iceman. I'm pretty sure that's how they dated him. Maybe it was. Who knows? Usually it's carbon-14. The carbon dating, that's what it involves. Carbon-14 is like a radioactive isotope of carbon, and the decay of it. The decay of it would result in like how much of it is missing. Shows you how old it is. And premature third thing. Industrially, you can use X-rays. Again, X-rays, yes, to scan materials for imperfections. So you do a weld, you put it in a scanner, and then you bombard it with X-rays, and you get to see the weld inside and out, and you know if there's something missing, something broken, there's a crack, maybe. You get to see if there's any problems. So pretty useful. Now, what is nuclear structure? I've already kind of explained it, but I never actually gave a concrete definition. It's the arrangement and behavior of protons and neutrons within an atomic nucleus. That's the definition. Nuclear structure means structure of a nucleus. Simple as that. The study of it encompasses formation of a nuclei, like how it's made, what makes it up, energies involved, and the decay of the atomic structure. Radioactivity itself being kind of a subset of the whole nuclear structure study. And there's an image of an atom with proton and neutrons in the center making up the nucleus, electrons orbiting around it. It's not very accurate because electrons don't do that. They orbit, don't get me wrong, they orbit, but not like that. Not in clearly defined ovals. It's more of a cloud of probability. We can't really tell where the electrons are, so we just guess, yeah, it's most likely to be there. So it doesn't look like that. Now, we're going to talk constituent nuclear particles. What exactly makes up a nucleus? So it's made up of nucleons, the term itself referring to specifically particles inside a nucleus. So just neutrons and protons. Those are the nucleons because they're the only particles in a nucleus. Neutrons are called neutrons because they're electrically neutral. No charge. They don't do anything. They're just mass inside the nucleus. So they're neutrons, neutral. Protons hold a positive charge. The force that holds the nucleus together is called the strong force, or strong nuclear force. something. It's one of the four fundamental forces that physicists have decided to call. Gravity is one of them. Electromagnetic forces is the other. And then you have strong and weak force. Strong force is super short-ranged. It's only affecting the particles inside the nucleus. And it is strong force because it is very strong. Protons are positively charged. They don't want to be near each other because like charges push away. So how does a nucleus stay together if it's a tightly packed ball of neutrons and protons, and the protons don't want to be near each other? Strong force, because it's strong. It overcomes the repulsive forces of all the close together protons and holds the nucleus together. Now, another thing about protons is that they're used to identify elements. Elements are identified by an atomic number. It's the number that they are on the periodic table. Hydrogen 1, helium 2, lithium 3, carbon 6, stuff like that. It is the number of protons in the nucleus. Carbon has 6. Boron, the one before it, has 5, so it's number 5. Hydrogen has 1, it's 1. Helium 2. Simple, right? It's also, coincidentally, the same number of electrons that an atom has in its orbitals. Carbon, 6 electrons. Oxygen, 8 electrons. Simple. The mass number of an atom is known as the atomic mass number, and it is protons and neutrons combined. Protons, about one atomic mass unit. Neutrons, about another atomic mass unit. So you just add them together. Carbon, as an example at the bottom, has an atomic mass number of 12, since it's 6 protons, 6 neutrons. Now, nuclei and electrons have an interesting relationship. This is the passing mention that I talked about earlier. Electrons are attracted by electromagnetic forces, and they are pulled, them being negatively charged, are pulled directly to the positively charged protons. And that is why they're constantly surrounding a nucleus and forming atoms, because they want to be near these positive charges. And they float around them in the orbitals, which are regions of space surrounding the nucleus. And previous models showed like planetary style rotations, kind of like the image where they'd be in a closed loop around it. That's not true. It's like a cloud, like I said. But it was close. It was surprisingly close at the time when they couldn't figure out what exactly electrons did. It was believed they were circular, then they believed they were an oval shape, and eventually technology got good enough. We can say we don't know where they are. It's a probability cloud. That's best guess there. And here's the fun fact about fission and fusion. Now, you're probably aware of what these terms mean already, and if you aren't, this will be a fun fact. And it's still a fun fact even if you do know it. Fission means splitting. It means when nuclear fission occurs, a heavy unstable nucleus, or several heavy unstable nuclei, will be, individually speaking, split into 2 or more lighter nuclei, getting you smaller elements. And that releases a lot of energy and some neutrons that may ricochet and cause fission in another nucleus. That's how you get the nuclear bomb. The nuclear bomb works by causing a fission chain, where one goes through fission, splits off, ends up causing another going through fission, so on and so on and so on, until the energy builds so greatly, you get that wonderful picture. Found that online. Honestly, that's a really good picture. And that's how much energy gets released. Granted, that's not one fission, that's a chain of like a dozen or so, at least. But the point is, lots of energy. And that's just from splitting an atom. And you get that. It's crazy, really. Fusion is essentially the opposite, where you take 2 lighter nuclei, smash them together, you get a heavier nucleus. And that's how that the rest of the elements on the periodic table formed. How you got heavier and heavier metals, stuff like that. It's just atoms of 2 lighter metals smashing together gets a heavier metal. Little hard to recreate fusion on Earth because it requires such extreme temperatures, pressures, stuff like that, that you can't keep it up for very long, at least not with current technology. So scientists have managed to do fusion, absolutely, for probably a couple seconds. uh, that's because fusion, with all the energy you have to put into it, is most commonly found in the center of stars, like the sun, where they are constantly fusing things together. And that's how they stay burning. They're constantly fusing atoms together to create heavier ones, and that's how they stay burning, because fusion creates way more energy than fission does. Yeah, lots of heat, lots of energy, center of the sun. Now, what is radioactivity? It's a term that just refers to the process of decay undergone by a stable nuclei. When it's unstable, due to an imbalance of internal forces or just has too much energy in it, it will attempt to achieve a stable state by undergoing this decay. And it'll release radioactive particles, electromagnetic waves, something. Different kinds of decay characterized by what comes out. That's what radioactivity is. The decay of nuclei follows, well, there's three main types, which you can see here. There's alpha decay, where a nucleus will eject an alpha particle made of neutrons and protons, equal to a helium-4 nucleus. You have beta minus and beta plus decay. You got two of them, whereby it will decay into a different nucleus, releasing an antineutrino and an electron, or a neutrino and a positron. And then you have gamma decay, where it kind of just goes into a different nucleus and releases gamma rays, which are ionizing and not actually particles. They're rays, they're waves, they're electromagnetic waves. So not made of protons, not made of neutrons, not an antineutrino or a positron. So there's three types, the alpha, beta, and gamma. That's their distinctions. Greek alphabet, love it. Photons are what gamma rays are made of. More info on that in a couple slides. And they are massless, so they're not particles, because particles have mass. The stabilizing, nuclei stabilize because of this decay. It gets rid of energy, and getting rid of that energy makes them more stable. It's like if you had a seesaw and you had too much on one side, so you can't tilt it. Get rid of something, and if it's even, it'll balance out. So you can think of decay kind of like kicking someone off a seesaw, if you want. That's how you stabilize it in a way. I mean, alpha decay looks like it kicks someone off a seesaw. And the other thing about decay is that it will change the nucleus. Every single one results in the changing of the nucleus in some way. Most notably, you can see is alpha decay kicking out what makes up its nucleus, gonna end up a different element. Now, alpha decay, symbol alpha, one of the three types of radioactive decay characterized by the release of an alpha particle. Alpha particles are identical to a helium-4 nucleus made up of 2 protons, 2 neutrons. That's alpha decay. It just shoots out a particle. Now, because it shoots out 2 protons and 2 neutrons, it's going to change. Not going to stay the same element. Not at all. The process usually takes place in elements with atomic numbers greater than 82. So carbon, as number 6, is not going to undergo alpha decay. 82 on the periodic table is lead. So elements heavier than lead, essentially. And you'll get alpha decay. So greater than 82 probably won't go any lower than 82. So everything, that's actually the thing about alpha decay, is a lot of things decay to lead. Like a lot, actually. A bunch of radioactive isotopes, they'll eventually decay to lead. Now, alpha particles are heavy for a particle, but they lack penetration power. Can be stopped by a sheet of paper. So they don't travel very far in air either. They can't go through the skin, actually. They get stopped at the lightest layer. Now, beta decay. Symbol beta from the Greek alphabet, characterized by the release of beta particles. High speed, high energy, so they go a little further in air than alpha particles can. Unlike alpha particles, which get stopped by a couple centimeters, they can go, if I remember correctly, about a foot. They can be electrons or positrons. Positrons are the antimatter equivalent of electrons and as such are of opposite charge. Yeah, we're talking antimatter. So it exists, at least in the form of positrons. It's just an electron if it was positive. Yeah. In beta minus decay, if you remember there's two specific ones. Beta minus decay, a neutron is transformed into a proton, an electron, and an anti-electron, neutrino, which is a small particle of electron mass, no charge. Beta plus decay, it's actually reversed. Proton goes to neutron, shoots out a positron, opposite of an electron, and a neutrino, completely chargeless particle. Neutrinos, same as the antineutrinos, small in mass, no charge, opposite quantum properties. Antineutrinos and neutrinos, they're anti of each other. Beta minus, you go from neutron to a proton. Beta plus, you go from proton to neutron. So it's characterized. You get two types of decay in one category. Brilliant. And it's characterized by what comes out. Gamma decay. Symbol gamma. Gamma decay is characterized by the release of gamma waves, electromagnetic waves of highest wavelength on the electromagnetic spectrum. So on the electromagnetic spectrum, only a small section is visible light. Gamma waves are way past the purple end because the closer you get to purple, the higher the energy gets. Here's visible light, here's the full spectrum. Gamma's all the way at the end. Short wavelength, incredibly high energy, huge penetration power. They can go through a lot of things, and that is why lead is such an important element because of it has the ability to stop such highly radioactive rays. That's why so much gear used in like X-ray offices and everything are lead lined. Like if you get an X-ray, they'll give you a apron that is lead lined so you don't get ionized. X-rays are less energy than gamma rays, but they're just slightly further down, like here. So they're like the next down. So same applications essentially, same ways. Both are made of photons, which are massless and move at the speed of light. If you have a mass, you cannot reach the speed of light. Nothing with a mass can get to the speed of light because it would take an endless amount of energy to get that mass to the speed of light. That'll be fun. Gamma rays are made up of photons because they originate from nuclear processes. X-rays are also made of photons, but they're from electron transitions or deceleration known as Bremsstrahlung. Bremsstrahlung is electron deceleration when an electron is decelerated or deflected by an electric field, usually caused by a nucleus of an atom of some kind. And that releases an X-ray. And while still made of photons, not the same thing. X-rays don't come from radioactive decay. Gamma comes from radioactive decay. Don't get me wrong, X-rays still count as radiation, but they're not because of the structure of a nucleus in any way. They are caused by electron transitions, which in its way is still a radiation, but gamma changes the nucleus. X-rays don't. It's just the electrons fooling around. So, yeah. That's your explanation on photons, by the way. Stabilization. All these radioactive decay processes exist because an atom wants to be more stable. And it will attempt to do that in basically any means necessary. It wants to be stable. It wants to be a perfectly flat across seesaw. Too much on one side, too much on either side, actually, and it will kick stuff off, release energy, release particles to try and be stable. It does so by decreasing energy, getting rid of anything that it can just to be not an overflowing cup of water, really. The atom itself may be an entirely different element because of the changes. Kicking away protons and neutrons will completely revert it to a completely different element, which is how you end up with stuff decaying to lead. And the threshold of how many protons a nucleus can have before it becomes unstable is known as the proton drip line. You don't need to really know this. I don't even really need to know this, but I figured it would be a pretty fun fact. if the number of protons in a nucleus surpass this threshold, the proton drip line, it becomes unstable due to an uneven proton-neutron ratio, and the nucleus will then decide to undergo decay. So you can probably have maybe 1 to 2 protons more than the number of neutrons. Any higher than that, and you'll get decay, and it will kick out protons and neutrons until it's stable. And that's the proton drip line. Little complex, all of the papers describing it are also complex and way beyond what is needed in this presentation. But I include it because it sounds like a pretty fun tidbit. Now, weak force and quarks. This is where I explain how in beta minus and beta plus decay, you get different neutrons to protons, protons to neutrons. Weak force is one of the 4 fundamental forces. Gravity, electromagnetic forces, strong force, then you get weak force. It's responsible for changing neutrons into protons and protons into neutrons during beta decay by changing quarks from up or down. Quarks are a fundamental particle, meaning they aren't made of anything. Right there. Fundamental particles can't be made up of anything. They just exist. They are the smallest things get. And electrons are another fundamental particle. You can't break an electron down. Now, as part of the helpful diagram there, protons have 2 up quarks, 1 down quark. Neutrons have 2 down quarks, 1 up quark. And during beta decay, weak force will change them up or down. And by flipping one of the up quarks to a down quark, you get proton to neutron. By flipping a down quark to an up quark, you get neutron to proton. And that's how you get the change, because weak force changes the quarks that make up the protons and neutrons. Now, we're going to talk about how exactly an element changes when it decays. Helpful diagram too. Under certain decay processes, some elements may end up as entirely new elements due to loss of protons and neutrons. As you can see in the diagram, krypton 89 and krypton 90 can both decay to more stable states along rubidium, strontium, yttrium, resulting in completely different elements. You got krypton 89 beta decaying to 89 rubidium, then to 89 strontium, to 89 yttrium, which is stable. Underneath the arrow showing the beta minus decays, you see T1 half, 3.15 minutes, 15.15 minutes, 50.57 days. That is the half-life. The half-life measures how long it takes for something, a radioactive sample, to lose half of its total to decay. So from krypton to rubidium, it takes 3.15 minutes for krypton 89 to decay, half of it to decay to rubidium 89 through beta minus decay or whatever. All of it lost 100%. That's what the half-life is. And that ties back into carbon dating, because carbon-14, by measuring its half-life, I don't know right now, you can determine how much has decayed off. And that's how the half-life works in carbon dating, because by measuring how much decays off, you can determine how long has passed. And that tells you how old something is. These are all isotopes. They're the same element, but with a different atomic mass. They've got a different number of neutrons. They have the same number of protons. But the 89 is not the atomic number, it's the atomic mass number. Krypton is not 89. At least that's not its atomic mass. But this isotope has a atomic mass of 89 because it's got more neutrons than it's supposed to have. And these are specifically radioactive isotopes because they are not stable. They will radioactively decay, as in the diagram. Now, in case you noticed, krypton 89 stops one step before stops at 89 yttrium. But just by upping the atomic mass by 1 to krypton 90, you suddenly get beta decay past yttrium 90 straight to zirconium 90. And in case you haven't noticed, the half-lives are a lot weirder, because you have Krypton 90 has a half-life of 32.32 seconds, meaning in half a minute, you've already lost half your Krypton 90. And then rubidium 90 has a half-life of 158 seconds, so little less than 3 minutes, in a way. So you've got a little less than 3 minutes before you lose half of the rubidium 90. And then you get strontium 90 to yttrium 90, and it's 28.9 years. So in half an hour, you would have lost literally all of your Krypton 90 and whatever rubidium would have come out of it. Then you have to wait basically 30 years for strontium to go half of it to yttrium 90. And then it's only 64.05 hours until it goes to zirconium 90. So different atomic masses have way different changes. You will not have the same decay just because you add a neutron. You change one particle in a nucleus and you will get a completely different process. And that is kind of the fun part because it's such a different change. You throw in one proton, or one neutron, you throw in one neutron and you get 3.15 minutes, suddenly 32.32 seconds. It's not even half, it's less than half. But strontium 89 to yttrium 90 is only 50 days. But strontium 90 to yttrium 90 is 28 years. Anyway, time to recap, because I've covered everything I kind of want to say. Nuclei are made of protons and neutrons, surrounded by electrons, make up all matter, yada yada. Simple. If unstable, they undergo radioactive decay, characterized by the type of emissions. Then, elements can change into completely new elements due to the radioactive decay. Applications of nuclear structure and radioactivity range from medical use, military use, industrial use, and technological use. You can use it in a lot of things because the technologies created with these have such immense range of applications. Medically, you scan for cancer with x-rays, but you can also use those x-rays industrially to scan metals, or you can use it military-wise for sensors or some kind. You can use so much with what is discovered that's why it's so important to know why it's studied, because it applies to so much. Anyway, that's the end of the slideshow, and that's the end of my presentation. I'm Xander Manti. That's the end of my physics presentation. Hope you enjoyed. It was rough. See you around.